Okay, welcome to the Tech Talk. I am Davut Rafi. I am a visiting scientist in the search quality team, and I am pleased to introduce York Sander, who is visiting us from University of Alberta. York has done some interesting work in the past on clustering. Some of the papers his papers that are well cited, DB scan and optics, are like well known in the area. Today he's going to tell us what he's up to more recently. One thing I have to remind is that since this is an external visit and the talk is going to go to YouTube, so you don't want to discuss the details of your projects. So just some as a reminder. Okay, with that, so I will leave it to York.
Okay, thank you very much, Davut. I'm going to talk today about projected clustering, the way we have done it recently. So let me give you kind of an overview of the talk. So before I start describing what we have done, which will contain also an experimental evaluation, I'll briefly will introduce the problem. I'll give some motivation. What is this projected or subspace clustering? And I will also discuss some of the prominent approaches that have been proposed. I'll pick one of the approaches per kind of category. We'll briefly describe it so that you can see how this relates to other work that people have done before us. So my hopefully only 30-second introduction to clustering. I'm assuming you know a little bit what that is. It's about finding groups in data. So it's not a well-defined problem, and there's two major intuitions if you look at the literature about clustering. You could categorize them in approaches where the intuition is that clustering is a partition of a set of objects, so that objects within one class are more similar or more related to each other than objects from different classes. Typically, approaches that fall into this category try to define an objective function and try to optimize that function, finding the partition that optimizes that. There's a different intuition. Some argue maybe that is not even clustering. I've had discussions like that. I've done work in this area of clustering, where you assume that the clusters are kind of dense areas in a data space separated by regions of lower object density. So if we look at this picture here that illustrates in 2D some of the cases, what that means. Here, you would argue, according to the second definition, this would still be, you would still call clusters. Yeah? But not according to the first definition, because obviously, if I allow this to be a cluster, there's obviously no limit on how dissimilar objects within a cluster can be in given applications. Typical usages, it's kind of related to density estimation. You want to get some insights into the data distribution. Pre-processing step for other algorithms. You can think of this also as a data compression if you replace the data with the clusters that you found later to do follow-up analysis. Now, what is the problem? Why do we need something like projected clustering? No, I'm sorry. I still have to explain this slide here, which shows that virtually all the methods, even those based on this notion of point density, use some kind of dissimilarity function, similarity or dissimilarity distance function that typically considers all the attributes of your data after maybe some appropriate feature selection method that you've applied before. But once you have a set of data, you assume all these attributes are relevant for all the clusters that you're looking for. And here's just some examples of distance functions for numerical attributes, like an LP norm. If for p equals to the Euclidean distance, everyone knows that here's something based on the cosine of the angle of the two vectors, if x and y are vectors in this case. For categorical attributes, something is an example here, the simple mismatch coefficient, just counting how often do they disagree. Yeah. Or for sets, if your objects are sets, you can do something based on a Jacquard measure, intersection over union. As a distance would be 1 minus that. Yeah. However, if we do this in all dimensions of a data set, there's a problem when the dimensionality increases. One of the results that was obtained here in the database area is that as the dimensionality increases, under very general conditions on data distributions in high-dimensional spaces, then in the context of querying data. So you have a query, you want to find nearest neighbors of that query, for instance. It can be shown that under those very general conditions, the difference between the maximum and the minimum distance of objects to that query vanishes. Yeah? So that means that clusters become less and less meaningful the higher the dimensionality. So on an intuitive level, you can also argue, well, yeah, if I look at similarity between things, and they can now vary in 1,000 different aspects, can be similar or dissimilar, and I aggregate all of those. Yeah, so what does it really mean? So an object is maybe more similar with respect to this subset, but then dissimilar here. Another one, it's the other way around. And so, but if I aggregate this over all the attributes, every object is approximately equally similar to your query. So this is on an intuitive level. There's other things going on in high-dimensional spaces that are collectively referred to as the curse of dimensionality. Some of you might be familiar with other aspects that you encounter in your work. Yeah, and so this is one of the reasons why people have started looking into something like projected clustering, especially also in the context of nowadays the possibility to just collect data almost blindly, because you just can. Clustering has been studied in statistics for a long time, and this wasn't really a big problem because the data was collected based on an experimental design that had a specific scientific question in mind. So you were selecting already features that were with high probability relevant for your task. Whereas in many applications nowadays, you just have instruments that allow you to measure, sensors, and you're collecting all this data, and afterwards you want to find groups of data or whatever. And now in a much larger set where you don't really know what is what is a relevant attribute, what is an irrelevant attribute. Yeah. So even if you assume here's one case how irrelevant attributes, if we just for the moment assume what we know what that means, saying that we have here two clusters in 2 dimensions. So if I somehow would know that these are the 2 dimensions, I collect the data, a clustering algorithm may be able to find those. Now, if I don't know these are relevant, I just managed to get a superset of those attributes. And many of them that are included in that set are irrelevant. Like here is one, a D3, in which the values of that attribute for the objects are kind of random. Yeah? That will kind of dilute the clustering structure. And the more I add, the more diluted this whole situation is. And feature transformation, global feature transformation, can often not solve this problem, which is why people have looked at projected clustering. Now, my motivating example is not text data, because we haven't been successful. Well, we haven't done it yet because of there's challenges in the data pre-processing with text that the students and I haven't been avoiding so far. So my motivating example is gene expression data. So who knows what gene expression data are, or who doesn't know gene expression? I'll try to give a very brief explanation of what that is. So the cells, they produce proteins to do whatever tasks the cells of your bodies do. To produce a protein, it has to be assembled from like chemicals that are in the cells, and the instructions on how to assemble it are encoded in the DNA. I mean, so much this kind of knowledge about that I assume everyone has. So now, to get the information how to assemble a gene from the DNA to the kind of factories in the cell that actually make that protein, the sequence that encodes the protein has to be copied, translated, and so transcribed, and then these snippets that float around then to the factory to make that protein, you can measure how many of those float around. And you kind of are in a measure, in a sense, that's the assumption, they measure also the abundance of that protein, but it measures at least how many of these gene, the encoding regions are floating around of a particular type. They're easy to measure in large quantities. So you can measure thousands of genes, typically on these microarray chips. And what people are doing is they measure the levels of different genes under different conditions. And conditions can be different patients. It could be different tissue types, like heart, liver. It could be different experimental conditions that you take the same tissue and expose some of it to certain chemicals, others you don't. Consecutive time points when you want to do something like cell cycle, etc. Now, the problem with this is very high dimensional if we want to cluster the samples in some sense, because the genes are in the order of thousands, whereas the samples are more difficult to obtain. And I was even with here this order of magnitude optimistic, that you only have that in some of those cases. Often you have even less than that. Now, clustering, you can apply clustering to the rows or the columns in that matrix. But in any case, what makes this a difficult problem, why cluster analysis is difficult. You want to find groups, but it's not that simple. Genes are involved in more than one of the processes or functions. The same gene encodes a protein, but that protein is involved in different functions. So similar expression doesn't necessarily mean similar function. It could be expressed for different reasons. A single condition, what is called a condition, is often defined on a rather high level, like a doctor looking at a patient and saying, oh, he has a big tumor. This one is a small tumor. Or it's based on like some phenotype. That may itself already be a condition that represents several different subtypes. Only a small number of genes relative to the total number is involved in any of those processes, any of these specific processes. And only a small number of genes could characterize a different condition. So what does that mean? It means that what are interesting entities to find are actually subsets of genes and subsets of those samples that are related to each other. And this is what kind of motivates this idea of projected and sometimes called subspace clustering in the database community. There is another notion, just I want to mention that, something called subspace clustering, that it's related but a little bit different than this approach, where here subspace means really subset of dimensions. Subspace could also mean that you're looking for kind of a manifold, a lower dimensional in the data. Okay, so so it's different from full dimensional clustering that data may form clusters only in subsets of the dimensions. This is basically trying to get rid of irrelevant dimensions for certain conditions. If you want to find those subspace clusters may exist in different subspaces. That's also different from full dimensional clustering. So you may have a group that is characterized by one subset of dimensions, and another subset of dimensions characterizes, which in this example maybe another set of genes characterizes the process, a different process. These subspaces may overlap in terms of dimensions and data objects, which makes this actually a very difficult problem. And so there's major approaches that have been proposed recently. I'm only going to talk about the first one in more detail. The second one I will mention as well, but not in that detail. First one is simply called projected clustering. The second one is density-based subspace clustering, and then linear and nonlinear correlation subspace clustering, and this finding manifolds in the set would also be a category there. So what's the first one? In the first intuition, a projected cluster is simply a pair of two entities, two sets. One is a set of objects, the other one is a set of dimensions. And the idea here is that the points that are in the set Ci are closely related in the subspace formed by these dimensions in Di. That's vague. And we will see that the different approaches have to make decisions of what that means, closely located or closely related. So the problem would be to partition our data set into k such projected clusters, or to find a number of k of those clusters. Here, this is kind of the illustration. Again, I'm showing here in 2D, we have this cluster. If we go to 3D, there's an irrelevant dimension here. And you only want to find, in this case, to characterize this set as a projected cluster, and this C would be the set of these objects. There's no other objects here. And D would be only containing these two dimensions, not all three. Now, this density-based subspace clustering is an idea that is based on the second intuition of clusters, where it assumes that points in the cluster are now located in regions of higher point density than in the surrounding area, but only in the subspace formed by the dimensions in Di. I try to illustrate here only the two-dimensional projection, not the 3D, and try to illustrate that now the closely located is no longer really necessary. They can be far away, as long as there is a region that has a kind of a boundary that you can detect. So these approaches try to find now all subspace clusters in all subspaces with respect to some density parameters, and plus possibly outliers. Now, let me just go through a few of those approaches so that you get a feeling for what has been done. So I think the first one actually is this Proclass that has been proposed. It's a k-medoid type algorithm. If you know k-means, it's inspired by a full-dimensional clustering algorithmic schema that tries to iteratively refine an initial partition by improving some objective function. In this case, the medoids are objects that are kind of central in a cluster, represent the cluster. So what the algorithm does, I'm just giving you a very rough idea. I'm not going into the details too much. So for each cluster, so somehow there's an initialization. So you have already somehow clusters in the beginning. You have to pick them using some method. And the paper proposes some heuristic for doing that. You use the points to select attributes. If you think of the problem finding projected clusters, if you would know the points of a projected cluster, if it's truly one that satisfies this intuition, it would be relatively easy to detect the dimensions. You look at the distributions in the different dimensions, you pick the ones where that satisfy. However, you formalize now this idea of being closely related, and others that don't satisfy you declare as irrelevant. Now, this is basically assume you have already points somehow. Then you can do this, and this paper proposes the ones to choose the ones with the smallest standard deviation as relevant. And then once you do that, you have kind of the subspace, and you can now measure distances in that subspace. And you can recompute distances now of points to the central points in those clusters using their subspace and assign them to the closest. That gives you a new set of points. And so you can iterate at this point. You could do again, well, maybe we have to now refine the attributes because you have now possibly new points. We have a new distribution. There's something here going on. That if clusters start having too few points because they don't, in their subspace, there's nothing close anymore, you throw them out and replace them with other ones. And so it goes on. until it terminates according to some criterion. There is an objective function that is trying to be optimized here. Parameters are the number of clusters in average projected cluster dimensionality. So the problem when you try to cast this problem in the way that you optimize a function with is that, and this paper isn't particularly successful in that the objective function may have a trivial minimum. That's why you have here this other parameter. It tries to avoid clusters having only one dimension. That's why you have here, in addition, the average cluster dimensionality that kind of prevents clusters from having too few dimensions. And because you can show with the objective function, without this parameter, it would have an optimum where each cluster has only one dimension. There's another version. This is basically one approach that is inspired by this partitioning approach. There's another approach to projected clustering which formalizes this idea differently. So in this case, the idea of being close is simply translated into a threshold on the distance between points. It says that they have to be contained in a hypercube of side length W. So that's, and it has to be at least an alpha fraction of the points to be called a projected cluster. And then there's a quality function which kind of combines the number of points and a number of dimensions in some way to tell if you show me two, that I can tell which one I like better. And then it tries to find one cluster at a time. One entity called projected cluster in this sense at a time by picking a point, picking a set of X points randomly, and then checking for which dimensions all these points that I've selected randomly lie within W around that initial query point or seed point. These are my relevant dimensions. And then once I have the relevant dimension, I take the intersection of all these intervals. So I take all the points that fall into that cube in this dimensionality. And if I have enough, then I have already something that satisfies this condition. And I do this several times, and then I report the one that has the best quality in this process. There's some guarantees. It may look a little bit weird when you think about it, but the paper shows that there are some guarantees. If there is a projected cluster in this sense, you can actually find it with high probability with this approach. But so here's other approaches. The one on the bottom actually recognizes that if you want to solve that, you can actually have a deterministic algorithm based on, if you cast this as a frequent item set mining problem, you can find the best one with respect to this measure directly. You don't have to do this randomized approach. Okay, so this was one. Another one, if you know clustering a little bit, the landscape, there's hierarchical clustering as well. Now, of course, you can try to do something hierarchical. This is the method HARP. It's doing something that all the hierarchy, or almost all do. They start by the agglomerative algorithms, at least. They start by having each object in their own cluster, and they start merging then closest pairs. Now, in this case, the condition for merging is a little bit different. It looks at how many relevant attributes it has. And the relevance of an attribute is based on a complex function that compares basically the local and the global means and the variances of the points in the cluster versus all the points in that subspace then. Now, there is two parameters, so it says, well, they're merged if there's at least d-min many dimensions, and if this relevance score is greater than this r-min. And those parameters change during the iteration, so it starts with being very restrictive in the beginning, and it relaxes at the end. And builds a hierarchy until it has a certain number of clusters. That's another approach. The one here, I mentioned only because we have it in the performance evaluation, and it performs among those that have been proposed pretty much the best. It uses the same objective function, or the same relevance score as HARP, but is based on an algorithmic scheme that is rather like Proclass, the one that tries to find an optimal partition. Okay, I'm thinking that I will skip the density-based subspace clustering algorithms here and move on to our own work after I briefly mention here the limitations and some of the limitations that we try to overcome in our approach. So they depend on the parameter settings, which, well, it's not necessarily a limitation. Sometimes it's desire to have certain parameters that you can tune. But there's parameters that are really hard to set in some of these algorithms, the alpha and the beta. How do I combine weigh number of attributes versus number of points in a projected cluster? It's kind of difficult to know what to do with these algorithms. In the experiments, it turned out that they really have a hard time finding really low-dimensional clusters with only a few relevant attributes. The algorithms ideally should be able to detect the number of clusters automatically. And something that has to do with the way these algorithms compute certain measures. They make them only suitable for numerical data. There's only few works for categorical data. The work that we are proposing can be extended. I don't think I have time to talk about that extension here, though. Okay, so it's called P3C. I think it stands for projected clustering with cluster cores. There's the 3 C's in there. So what we try to do is something that is robust with respect to parameters and has a small number. It has one parameter in essentially. It discovers very low-dimensional subspace clusters embedded in high-dimensional spaces. It's robust with respect to noise. It's scalable with respect to the database size. Unfortunately, not so much with respect to the subspace dimensionality. So small really means here absolutely small, not relatively small to the overall dimensionality. It can allow overlapping clusters, and it's extensible to categorical data. So I'll give you the overview first, and then to talk about the details later. So the way we try to find projected clusters is we try to find something like what we call a cluster core, like a big chunk of objects that hopefully belong to one of those projected clusters. If you can do that, then all the other tasks become easier. You can refine this. It's easier to detect the relevant dimensions, etc. So, and we do this in a way that we start with one-dimensional projections. So we look at the distribution in the one dimensions, and we try to find intervals that somehow could correspond to projected clusters somewhere in higher dimensional. Doesn't have to be just one. It could be, because you're looking at very low-dimensional projections, could be an interval that contains two clusters in some higher dimensional space or something like that. But taking those one-dimensional intervals on the attributes, we're trying to determine cluster cores, which are sets of intervals from different dimensions, hopefully then representing only one cluster at the end. And refinement of these cluster cores can be done then with a standard clustering algorithm, the expectation maximization clustering algorithm. Outlier detection is optional, can be done after refinement. And once you have clusters, identifying the relevant dimensions becomes very easy. So first, one-dimensional cluster projections. What do? We basically divide the interval into bins. We're trying to do a statistical test. We check, are the values in that attribute randomly distributed or not? And if they're not randomly distributed, we look for the regions of high density. Idea being that if they are unusually high, they contain possibly projections of clusters. So in this case, the outcome will be the red arrows here. So on this attribute, we find these two intervals. On this attribute, we will find this interval using a simple chi-square test. So how is that done? It's done bin by bin. So when we look, it's non-uniform. We look for the bin with the highest density. We mark it, and then we repeat the test with the remaining attributes to collect all those bins that in the end have unusually high support. And then we merge adjacent bins into intervals. Okay, having those intervals, we want now to combine intervals from different attributes to cut out chunks in higher dimensional spaces. Now, how can we do this? So if we assume we have already a set of dimensions of some intervals on those dimensions, when do we add another interval that is not yet in there? There has to be some evidence that it represents the same cluster. To measure this type of evidence, we're using the expected support as computed as following. If we assume that we know the actual support means number of points in that region, we know that. Now, assume that this interval, the dimension where the new interval lies on, is irrelevant. Irrelevant in our model means that the values are randomly distributed. That means if we add this interval from this, we would only expect proportionally to the width many points to remain in the set, in the support set. So that's what it means here. If we take that set, only proportionally many to the width of that new would fall into the set where we add this interval. That's the expected support under the assumption that this is irrelevant, and irrelevant means randomly distributed. Now, we can say that now evidence that S represents the same cluster exists if the expected, the actual support is significantly larger than the expected support. What does that mean? Significantly larger. The way we modeled this was we say, of course, it's larger, but then how much larger? We model this as we assume that that there is a Poisson process, if you will, with this expectation. When you have a Poisson process, so with a particular expectation, this distribution basically gives you the probability of seeing this actual support when this is the density of the process. And we give this is the parameter that we introduce in the system, that we have to set this to some small value, that we want to have a very low probability of actually seeing this, the number of points that we see once we add that new interval versus the one that we would expect under a uniform distribution. Okay, so that's how we measure the evidence. Now, what is a cluster core? A cluster core is defined as the set of intervals that consists of only and all the intervals representing the projections of the same cluster, but in the following sense. It means not just there is a way of adding intervals in one particular order so that I get a set where I had in each step evidence for adding it. It has to be, we define this in a little bit of a stronger way. We say that for every subset of this S, it must hold that there's evidence that adding the other, another one in S, that it represents the same cluster in the sense as defined on the previous slide. By doing this is a little bit stronger than maybe necessary, but it allows an algorithm which is a little bit more efficient than exhaustive search. Those of you who know how to find frequent item sets, there's this algorithm called a priori. This algorithm can be used because this satisfies a downward closure property. So if a set does not satisfy this condition, no superset can satisfy it. So I can, in a search space, exclude that whole branch from search. And the second condition is that for any interval that is not in S, so this is kind of a maximality condition for a cluster core, it contains all of those. So there is no interval for which there's no evidence that it represents the same cluster. Okay, so having these cluster cores with an a priori-like algorithm, once we have them, we can refine them by simply, let me back up. So once we have cluster cores, they're basically defined as by some dimensions. It's a hypercube in space plus the points that are in that hypercube. So giving those points, we can now assign other points by estimating a mean and the covariance matrix of that set of points, and then we can use Mahalanobis distance to see which point of the remaining points, where do they fit best. Yeah? And once we have that, we can use like an EM clustering algorithm to just iteratively refine those cluster cores and afterwards derive either a hard or a soft partition. Hard meaning we assign a point only to the most likely cluster and most probable cluster. And a soft partition would allow membership in several clusters if the probability of belonging there is greater than 1 over k. After we're done with that, we can do multivariate outlier detection, meaning we can throw out points that have very low probability of belonging to any of these clusters. And so, as I said already, once you have clusters, you can basically throw out irrelevant attributes again by looking. Those that look uniform are irrelevant. We only keep those that are non-uniform in the end. Oh. Okay. Now, so the last part will be just showing some experiments that we did here on synthetic data that we've generated according to a generator that was proposed in these papers that I mentioned, like Proclass, etc. So we have 10,000 objects. We have 100 dimensions. We have an extension for categorical data. That's why this is still on here. I took out the slides because there's not enough time to talk about it. We implanted 5 clusters having 15 to 25% of the points, 5% are outliers. And the distribution within the clusters, we have 2 categories. One where we distributed them uniform in a little box, and one where we distributed them on a normal, like a multivariate normal, like a little ellipsoid somehow. We have another set of or another distinction in the experiment where we have when it's axis parallel versus rotated. That's something that has to do with some of the algorithms make that distinction and specialize on these that rotated clusters. Okay, so this is just the setup here for the synthetic data.
So what was the cluster dimension?
The total dimensionality is 100. And the subspace cluster, good question, it's not on the slide. Not larger than 10, that I remember. I don't know the actual, unless we start varying. There's one experiment where we actually increase the dimensionality. But for the other, where the subspace cluster dimensionality has to be constant, it's probably something like between 2 and 10, different cluster dimensionalities. Okay, so we have as algorithms that we compare ourselves with, the ones that I mentioned here, plus other ones for categorical data. It is on those slides. I won't talk about it because I've decided not to present the extension to categorical data. When we look at the results of the other algorithms, we had to set their parameters. So what we did was for those values where we know the supposedly true value, like number of clusters, average subspace cluster dimensionalities, things that we could compute, we set the values to the true values. But there's numerous other parameters that have to be set, and we tried several based on the heuristics suggested by the authors, etc. And played a little bit and chose at the end the best results we could get for those. For the accuracy, since we generate the data ourselves, we have kind of labels and allow us to measure with an F measure which is the F1 measure, like the harmonic mean between precision and recall. So we first, for each cluster that we find, we try to find which of one is the best match. And from that, we can basically compute precision recall. And then overall, if we average this over all the clusters and over 5 runs, we get the numbers that are presented on the following slides. Here is the first slide is just showing that once you set this threshold for the Poisson probability to a small value, there's no influence that this parameter would have anymore on the cluster quality. This shows kind of the robustness to this parameter. And here we have now these, the quality of these pictures is worse than I was hoping for. We see now results for the accuracy for different categories. When you look at the heading here, category uniform equal parallel means that we have the points in the clusters distributed in a uniform way. All subspace clusters have the same number of dimensions, has the same subspace dimensionality, and they're axis parallel, so we didn't rotate them. The other category, that's the other extreme combination, where we have normal distributions, and the subspace cluster dimensionalities are different. So one subspace cluster had only 2, the other one might have had 10. And they have been rotated. We can see that like the overall behavior of many of the algorithms is similar. Or let's say they fall into 2 categories. Those that eventually start working and those that seem to never really work. Ours are here, the blue and the red one. One is for hard partitioning, the other one is the soft partitioning variant. And we can see that those that work start working once the cluster dimensionality. This is F1 measure measured here for different average cluster dimensionalities. Once we reach here 20% of all dimensions, those algorithms that work well, work well. But this is also the case, 20% of the dimension, that's when the full dimensional subspace clusters also start to work. They will be able to recognize those clusters in the full dimensional space as well. I just want to give you like the overall impression. I don't want to discuss all the details here. What the point here is that in those experiments, in those cases where that we wanted to improve, we improved over the previous work, finding the subspace cluster when the subspace cluster dimensionality is very low. And this is for categorical data. I'm skipping this. It's robust to outliers. That's what these figures show. If we increase the percentage of outlier, the results deteriorate somewhat, but not dramatically. And it scales well with respect to the database size, but not so well with respect to average subspace cluster dimensionality. And the reason is that it has this a priori type algorithm, which like for frequent item sets, you start combining one element sets then into 2 element sets, etc. And you can only exclude something that does not satisfy this condition because you have this anti-monotonic property, meaning if you have something that satisfies the condition, that doesn't satisfy the condition, no subset can satisfy it. But it also means that if I have something that satisfies it, every subset will satisfy it. And I have to work my way all the way up to this. So it's exponential in the dimensionality of the largest subspace that I have a cluster in, the runtime. OK, so we did some experiments on some real data. That's often a little bit difficult to find good real, what does it mean, good real data? Real data where you can actually measure the quality of what you did, because you know you need something like labels to compare this to a kind of a ground truth. And so we picked some data sets from gene expression data, colon cancer data set, where we had 2 classes, tumor and normal colon tissues, 2,000 human genes, and we discovered 2 clusters, each had a dimensionality of 11. And here's the accuracy of all the algorithms. Another data set had 2 classes. We only found 1 projected cluster of dimensionality, 2 with an accuracy of 68. But I think if we look at the numbers, that's really not much better than random, because that's about the percentage of the 1 class that you would find by randomly picking points. Okay. So conclusions. Well, it's robust with respect to the single parameter. It's suitable for categorical data. We haven't really discussed that. And it allows us to discover very low-dimensional projected clusters, but has, unfortunately, an exponential running time in the largest cluster dimensionality. So it's suitable only for low-dimensional subspace cluster in an absolute sense of low. Okay, so I want to mention that also this is joint work with Gabriela Moise, one of my PhD students, and Martin Easter from Simon Fraser University. And if you want to read more details and results are in the paper cited here on the slide. Okay, thank you very much. And if you have any questions.
Keep going through it on a regular basis.
Yeah.
Whether it is or isn't documented, it looks wrong.
Okay. Well, I guess I will ask one question. I mean, I can see that this is for multidimensional data, and one question is that if I want to take something like this and apply it to text, like, what are the issues? I mean, are you expecting, this thing to work on text, or if not, why not?
Well, I'm thinking that the ideas of a projected clusters are relevant for text clustering. The problem that I see here is rather that the dimensionality, it depends on how you represent the text. Yeah? But if we say like word frequency, so the individual words are my dimensions, then I have really a huge dimensional space, and even the subspaces in which I expect then clusters to exist will be rather large. Yeah? With a suitable pre-processing, if you look at rather than individual words, maybe n-grams or something, maybe it's doable. I haven't tried. I think it's probably, well, let's put it this way. Another thing that might prevent applicability, and this is kind of, something that wasn't probably very clear in the presentation. There is this assumption of what is an irrelevant dimension, and that is assuming that the values are randomly distributed in irrelevant dimensions. In real data, this, at least data sets we looked at, this is often not the case. So in real data, what you find is that the irrelevant dimensions have some distribution, often normal, instead of random. And so that's one of the things. This makes assumptions about the distribution. We're working on relaxing that, and that hopefully will broaden the applicability of this approach. And for text, I don't know how these the frequencies of words are probably also not random in a way. And well, that answers the question, I hope.
Another question. Okay, so let's time this video around the time.